Okay, so today we're going to be talking about some interesting things. So I'm going to be talking about this particular concept called RAII. We may have briefly touched on it in HLP2. It doesn't matter which instructor was teaching you, but we would have probably come across this particular topic, but not to the full extent. And then I'm going to talk to you about a sort of like an interesting optimization that is performed by compilers. And uh, it could be pretty useful if for your projects. So, and then it also leads into the discussion on Mu semantics. So I'm not sure if I'm able to get into Mu semantics today, but that will be definitely this week. All right. So the whole idea behind RAII is resource management, and it connects to exceptions. So I'm assuming that all of us know basic classes, class design, and I also assume that you know try-catch, the try-catch mechanism, and some basic idea of exceptions. In HLP2, we did a tutorial and an assignment on exceptions, and I checked, everybody got 100. So I'm assuming everybody is pretty good in that particular topic. Okay, let's begin sort of like from the very beginning. So when we think of resources, we are thinking of all kinds of different kinds of resources. Memory is the one that we are most familiar with. Very soon, you're going to be familiar with threads. If you're doing any sort of networking, then you're looking at sockets, obviously file IO. So all of you are familiar with C file handles, which are sort of encapsulated in C++ using streams. And if you're doing any sort of low level programming on the Linux or Unix environment, then you would have probably come across, or you will come across something called POSIX file handles. So there are many different kinds of resources. But basically, this is how functions work. They acquire some resources and they perform some operations. And the critical thing here is to free the resources that they claim, all right? Because all resources are finite. In essence, if you're looking at the previous week's assignment, if you take a really large file, okay, on the server and say, I want to split it up into files that are 2 byte, it's going to give up after a while because it cannot generate that many file handles, right, at once. So everything is finite. The number of threads is finite. The number of socket connections is finite. And so this is going to become a fairly critical part of your future career. If you're making a game and I'm the one who's playing the game, my game can crash, right? And I can restart. But if this is sort of something, if you're doing something related to the servers, the cloud, where certain information related to players and the statistics are being stored, those are details that you cannot lose. So you cannot just assume, well, if I don't have enough memory, I'm just going to crash, right? You may have to log the current status of the status of the game, all the players, and then gracefully crash. So RAII sort of connects to that particular idea where, sure, we want to acquire resources, but we care about making sure that the system can gracefully degrade if there is no possibility of the application moving forward because certain resources are not available. So there are two ways in which functions can manage resources, and quite a bit of the work that we did in HLP2 relates to pointers. So we especially spent quite a bit of time using the new and the new array operators in conjunction with the delete and delete array operators to kind of understand, runtime demands on your memory, the heap, the free store. And the second thing that we don't normally explore, but that is going to become quite critical as the lecture continues, is how do we manage resources using local objects? What do I mean by local objects? Well, you get inside a function, there is a object that gets initialized on the stack, and when the function returns, all of the objects in the local scope of that particular function are going to be destroyed by calling the destructors. So there are two ways we can do that. And first, I want to show you how things work with pointers, sort of a review, and then we'll talk about the other detail which is related to local objects. So here's a typical use of pointers. So here, rather than defining an object X that is local to this function F, we decided we'll use a pointer W to instantiate an object of type X. And at a later point of time when the function returns, well, the idea is that the programmer has inserted the delete call operator, and obviously the object sitting on the free store is destroyed. So the picture sort of looks like this, right? So W is a pointer pointing to some complicated object X. So I just drew some sort of a picture that illustrates that the object X is acquiring resources, right? So you can see that W is pointing to an object of type X on the heap. That particular object has no name, and that object itself has allocated for itself some resource. All right, it could be memory, it could be whatever, it doesn't really matter. And the basic idea here is that, and this is kind of what we spend quite a bit of time in HLP2, is, hey, we got to make sure we terminate, we call the delete operator before terminating from the function. So we also spoke a bit about, why functions like F are a huge source of trouble, right? Because they cause three specific problems. First one is called leaked objects, where the programmer might forget to call it delete as a or it could be that they prematurely delete, and I'll explain what that means, or, and this happens quite often in complicated functions, the programmer might end up double deleting and completely destroying the heap. So let's take a moment to kind of look at these, right, as sources of real trouble. Here's the first one. The programmer forgets to call delete. Well, what happens is that the object W goes out of scope, and everybody knows that the delete is not going to be called automatically just because W is going out of scope. So we end up with, a sort of like leaked object that is sitting on the free store. And notice that this object X of type X is complicated. So it itself has allocated a whole bunch of resources, and those resources will never get freed unless the program restarts, right? So this is fairly typical. People use new and then forget to call delete, and that's why tools such as Valgrind are quite useful to find these sorts of bugs. Premature deletion, it's a very sort of insidious problem. So follow the code here. You can see that I have P1 that have allocated an object on the free store that is pointed to by P1. And P2 is also pointing to the same object. Now, this happens actually quite frequently. And I'll give you a very simple example that comes from computer graphics or video games. You load up a lot of data about a particular level, right? When the level is when a player wants to go to a new level. Now, there's quite a bunch of data, and that particular data needs to be organized in many different ways. So, for example, in 3D, you may have an AI system that requires the data in terms of a quad tree. Your collision system may say, okay, I want that in terms of an octree, and so on and so forth. But you don't want to replicate the data. So the data is sitting somewhere in memory, and you have all these different pointers that are pointing to the same data. And these pointers are parts of a tree, a graph, all kinds of different data structures, right? And so this is a fairly common thing in any program that doesn't want to, acquire or waste memory, especially if you're looking at console games or embedded systems where memory requirements are fairly strict. And don't forget, the more memory you use, the more power you use. And so that is another constraint. So it's quite normal for two pointers, P1 and P2, to be pointing to the same object. And at some point of time, P1, prematurely deletes, right? It doesn't realize that there are other guys who are also pointing to this particular object. And part of it is coordination. There's no one person who owns this particular object. So it becomes difficult in a complex program to kind of organize ownership details. So in this particular case, both P1 and P2 are claiming ownership without knowing that there is another owner. And the original owner, P1, says, okay, I'm deleting the memory. And the way you want to imagine this is that there is some destructors that have been called, and the memory associated with that unnamed object that P1 was pointing to is sort of given up, and the free store has taken control of it. It's no longer under the control of P1 nor P2. Now, P1 is assigned the null pointer, so there's some sense of security, false, I should say, because when people read the code, they kind of, I've noticed that people assign the null pointer after you delete to give you that false sense of security, right? And then there is another object that gets allocated on the free store. This one is pointed to by pointer P3 that you see here. And it's entirely possible that the memory that was used for this particular object is now going to be used for this particular object. So ABC is taken over by XYZ, right? But P2 still thinks that it's looking at ABC, but what it is actually looking at is XYZ. And the whole thing is a colossal, disaster. And then P2 thinks it's changing ABC to PQR. But what it's really changing is P3's XYZ also to PQR. And so you can imagine the number of bugs that have been caused by the premature deletion. So this is a fairly common and significant problem, right? In any computer graphics application, any serious programming exercise, non-trivial programs, you have one collection of objects and many different ways in which you're going to organize the data, many different data structures. In some cases, you want them to be in a linked list. In other cases, a tree. In other cases, a vector, and so on and so forth. So there are many pointers pointing, and we need a clear sense of ownership, which is completely lacking here. right? And double deletion happens, well, basically, I guess I do use the term sloppy, and this is pretty sloppy, right? Hopefully it doesn't happen, and tools like Valgrind will catch these. And so this is again a pretty insidious error, because when you delete, unfortunately, the double deletion is going to completely screw up the heap, because in between, if some memory was allocated, right, and that memory is being used in the region that P was previously pointing to, well, when you say delete, there's a whole bunch of disaster that is going to happen in the background, right? I hope you're kind of getting the scale of the disaster. It's humongous. It's huge. So it's a tsunami of kind of like bad things that are happening in your code. Okay. So many in HLP2, what we did was we said, okay, these are all bad things. We kind of learned a little bit about Valgrind, and I think in some of the assignments you went and looked at Valgrind and so on. Okay, but there's one thing that actually plays a pretty significant role, and that is exceptions. Right? We didn't actually target that much, but that is quite significant, and it actually increases the scale of difficulty in terms of the programming. So here's a pretty simple exercise. So I used a C file handle. Sure, the F stream provides you an encapsulation of such a file stream, but I decided, okay, let's kind of use a C file handle. And I open a file and I use the file to read and write, maybe. In this case, just read. Now, I'm a good programmer, so notice that I terminate the function by ensuring that I close the file handle. So in other words, return the resource back to the operating system. But it's entirely possible that you can have some sort of a return in between. And let's assume that you took care of the returns, but it's entirely possible that some entity, right, might throw an exception. So the idea here is that even though the file is called use file, there could be a whole bunch of other resources that are being claimed. For example, memory. So you allocated memory, the free store says there's no more memory, and there's a bad alloc exception that is thrown, right? So when that particular exception is thrown, all of us have read about stack unwinding, which is what happens when exceptions get thrown, and the code will never reach this particular place, right? So we end up with a file handle that is completely lost. And remember, we are dealing with complex systems, server side. So in your game systems, you know, the economies, the player details, the game details. I'm thinking of big games like what's the one my son plays? Oh, I don't know. Epic Games. What's that thing, guys? What's it called? The one that got really Fortnite. Yes, yes, right. Okay, Fortnite. So huge game, and you know, lots of people can play together. So there's a lot of information being tracked, and you can't just shut the system down. So the you know, your game itself can shut down on your console or PC or wherever you're playing. Maybe you can restart, but you can't do that to the servers. So you know, this is a major problem that we never discussed in HLP2. And so what do we do? And here's one scenario, right? We learned about the try-catch mechanism. So here I go. I come into the use file and I say it's entirely possible that there could be some exceptions. So I'm going to wrap my use of this particular file handle in this try block. And then there is a corresponding cat. In case there is some sort of exception being thrown by one of the lines of code here, and notice I'm catching anything that happens, right? And then I come in here and I close my file. And does anybody know why we need to throw again? In this particular code, or what happens if I don't throw again?
Professor,
Mhm.
yeah, I think basically the catch will swallow the exception, right? If you don't throw again.
Yeah, but why throw again? Yeah, sure, you're right. We have to throw, but why? You're absolutely right. This guy will catch all of the possible exceptions. So I make sure that I close the file handle, okay? But why am I throwing the exception again? Why don't I just kind of,
to accommodate exception at the call site of this function?
call site? No, because um, you're actually you're so the throw is actually going to return to the call site, right? And the reason why we need to throw is because we shouldn't assume that it's only uh, an exception was thrown because of this particular resource. It could be that, there wasn't enough memory, so a bad alloc got thrown. We are catching every exception. My job is to make sure I close the file, but somebody's got to take care of the bad alloc. Or somebody wants to create a string where the maximum number of elements that can be stored in a string is being crossed. So we need to go and make sure that this gets thrown so that the appropriate entity can handle that particular exception. Am I making sense? Otherwise, we are not returning control to whoever can handle the bad alloc. We are, I think, as the first gentleman said, we are in a sense swallowing everything and saying there's nothing more. But there is an exception that was thrown, not necessarily by this resource, by some other resource. So I catch it to make sure I close this particular resource, but I need to throw the exception so that the appropriate entity can handle it. Did I make sense?
Yeah.
Okay. Now, obviously, this, as I say here, right? Verbose, tedious, because what if you have 10 different resources that you are making use of in this particular file? What are you going to do? Um, it's like you got to make sure that every single one of these resources is shut down like this one. And anytime a programmer comes along and adds another resource, somebody needs to go and add or hack, might be the proper term, and ensure that there are no leaks. So this becomes error prone, verbose, tedious, and the constant rethrowing is obviously going to slow down the recovery from the error, right? Because you are dealing with many different exceptions. So using the try-catch mechanism and to dealing with these individual pointers, it doesn't look like a reasonable way to proceed. So instead, uh, the idea is to kind of look at the general nature of what's going on. So we have all these different end resources. I acquire the first one, I acquire the nth one, I use these resources. And notice I'm releasing the resources in the opposite order. Anybody, can anybody explain why we are releasing resources in the opposite order in which we acquire them? Any guesses? And why it should be done this way? I mean, you're the programmer who's acquiring these resources, okay? You acquire 1 followed by 2 followed by 3 all the way through to n. Obviously, we are using these resources, but when you release these resources, you're very careful. You want to make sure that the last one that was acquired is the first one that is released. So you release in the opposite order in which you acquire. Any guesses, guys? The simple answer is there is a particular predetermined order in which I acquire resources because, when I acquire resource 1, let's say memory, okay? I'm probably going to use that memory when in conjunction with resource 2, which could be a file handle. That file handle is going to open a file and throw the information in that file into the memory that was allocated in the first resource, in the previous resource. So there could be these connections where resource M is relying on all of the resources before it, preceding it. And so therefore, when you release these resources, you got to make sure that you release the last one because it is the one on which none of the previous ones are dependent on. Because when they were given birth, when resource 1 is given birth, obviously none of the other resources were present. So 1 is not going to be depending on all of the ones that follow. So therefore, 1 should be the last one released because it has no connection to anybody else, but all the rest might be connected to it and taking advantage or using that particular resource. So this is a paradigm that is kind of, quite careful and carefully actually applied by C++. The idea that when you define objects in a class or members in a class, they're given birth or they're constructed and then they are destructed in a certain order. And the idea is that you chose a particular ordering because you wanted the previous ones to be alive when you come alive so that you can rely on them for certain resources. So this behavior, okay, is also something that is implemented by local objects. So in other words, if you acquire object X, X1, followed by object X, X2, and so on, X2 is going to be released first or destroyed first, followed by X1. So if this is the natural order in which we should be acquiring and releasing resources, then a lot of this particular work can be clearly handled by local objects that have scope within this particular function. All right, so that's what I mean by local objects, objects that have scope inside this function acquire. They come alive when acquire is initiated, and when acquire terminates, these objects are going to be destroyed. And so that leads to the idea that maybe pointers are not the best possible way in which we should be dealing with resources. Instead, we should be using local objects, objects that are constructed using constructors, that are initialized, I should say, using constructors, and destroyed using destructors. And the second thing I should tell you is that the entire exception mechanism in C++ is based on this particular idea. So in this particular picture, if all of these resources are acquired by using local objects, and if there is an exception being thrown here by any one of these objects, the exception mechanism that is built into the runtime environment of C++ will ensure that all of the objects that have been constructed to the point at which the exception is thrown will automatically have the destructors called, which means unlike with the previous scenario where we have the try-catch mechanism, in this particular scenario, we don't need to worry about anything. As long as you make sure every single object has a well-designed and well-implemented constructor-destructor pair, then the runtime environment will make sure to call the appropriate destructors if there is an exception that is thrown. And we don't have to individually kind of worry about, did I close everything else? So then in addition to closing PF, we may have to shut down some other file handles. We may need to return memory. We have to kind of watch for all of the resources, right? So you become responsible. While here, it's the runtime mechanism that kind of deals with making sure the appropriate destructors are called. So that is essentially what RAII means, right? And I'll talk a little bit more about it, but let's kind of look at how we can take the C file handle and just design a class, right? Just to kind of get us some sense of understanding in terms of why raw pointers are not the way to go, because obviously all of this will lead into move semantics, into smart pointers, and so on. So it's good to know why we want to wrap things into these classes. And let's begin with the, just take a moment to look at this particular class. I mean, I have the usual functions. Many of the classes that we wrote, okay? For example, the string class, the vector classes that you may have written in your assignments, you never had to worry about exceptions, right? If you ask for memory, you assume the memory existed, and you never had to worry about throwing exceptions. So it's entirely possible that when you are initializing an object, the resources may not be available, in which case you should be ready to signal that particular fact, right? And we'll talk a little bit more about it. So this is a constructor. This is a special constructor, guys. We haven't seen this before. Please take a piece of paper and pencil and write down the name of this particular constructor. It is called a delegating constructor. Notice the syntax. This particular constructor differs from the first one only in the fact that it takes a C++ style string, while the first constructor takes a C style string. So clearly, the implementation of both these constructors are, remarkably similar, right? It's only the parameters that are mildly different. So in C++11, we have the idea of delegating constructor where we can author other constructors using another constructor that has already been designed. So this is the constructor that has already been implemented, and I'm delegating the implementation and execution of this particular constructor to the constructor above, right? So we haven't seen that in HLP2. So just make a note of that. And this one is pretty trivial. So all of us know the purpose of using the explicit keyword. And one of the reason why I'm throwing these exceptions if P is a null pointer, it simply is because if you are initializing me with a null pointer, okay, and I'm a file pointer, I want to make sure that anybody who uses me, the file pointer object, doesn't have to check for the null pointer. We have to do that in C, right? We don't have to do that when I design this particular class, because when I initialized, I'm checking if I'm able to open the file or not. If it is not open, I'm done because there's no more work to be done. So that is the purpose of throwing an exception here. So obviously the rest is pretty trivial. We have a destructor here that closes the file, and then this is the implicit conversion, guys. we spent a bit of time in HLP2. Yeah, it takes a object of type file pointer and converts it into another type, right? And the name of the function, okay, it's weird. It doesn't really have a name, and the name is determined by the type to which you're converting the file pointer type to. Okay, all of this is good. There's one question I have for you guys though. When you look at this particular class, what do you think should be done with the copy constructor? Notice I don't have a copy constructor and I don't have a copy assignment operator. What is your opinion about these two member functions? Remember, we are designing this to avoid one critical thing that I spoke to you guys about here. Remember, I use the term ownership. One of the problems that is caused by this code snippet in function G is the fact that there is no clear owner of any one of these resources, right? P1, yes, did the job of acquiring the resource, but P1 didn't say I'm the only owner. Instead, it shared its ownership with some other guy called P2. But it forgot that it's sharing its resource, right? Or it didn't even know that somebody came along and shared its resource. So now we have two guys both sharing the same resource. And one of them decides, okay, I'm done with this, but I have no clue that others are using this particular resource. I don't know. I don't care. Maybe I'm going to just return. So that was, the problem that is being caused in terms of premature deletion. Now that you're aware of that, what do you think you would want this particular class to do? Obviously have a sense of ownership, right? So if you want to build that sense of ownership, then what should the copy operations do?
They be deleted.
That's very good, right? Because here you're saying, you know what? I own this file and I'm sorry, I'm not going to be able to copy this. So if anybody says I want to copy, well, the compiler will flag that as an error, right? So rather than a runtime crash, better to have a compile time error. So that is very good. And that is a critical part of everything in terms of how you want to manage your resources, right? So we'll talk more about it. And that's really what a smart pointer is. You take a raw pointer and wrap it, and we'll look at different techniques where the entire deal is about ownership and making sure that there is only a single owner or keeping track of how many owners there are. That's it, right? And we'll look at certain concepts behind that as time goes by. Okay, the beautiful thing though, from your perspective, having taken the raw pointer and wrapped it in this class that is class-based object that gets initialized automatically when it's instantiated on the stack by one of these constructors and destructed by the destructor, is that your management in terms of dealing with the resource becomes trivial. Notice we don't anymore need any of this stuff. We simply replace all of this with just this, right? So, when the object comes alive, F comes alive, it's instantiated by a suitable constructor. When the function terminates, the appropriate destructor is called. If in this using F part, there is an exception that is thrown, the runtime mechanism will make sure, since F is fully formed, it is a complete object because its constructor got completely evaluated, it will make sure that the destructor is going to be called. So this is basically one of the simplest things related to C++, I mean, we use the terms abstraction, encapsulation, and so on. But when it comes to resource management, it's as simple as that. Building classes that look like this, right? With the appropriate functionality so that you don't have to do this at in your code. Let's kind of look at more details. Like I said, if the exception is thrown, then the destructor is going to be automatically invoked. All right, that is the beautiful part of it. Okay, any questions, guys? All right, so this concept, okay, it's sort of related to data abstraction, encapsulation. It also relates to smart pointers. And Strustrup, the guy who invented C++, he came up with this sort of weird sounding name, right? It's a paradigm, and he called it resource acquisition as initialization. And to be honest, I don't quite understand what it means, right? Because if you think about it, what it does is that it helps you dealing with things that want to die because somebody called an exception, or because the function got terminated. You don't really need necessarily to construct this particular object when you give it birth, right? I gave you an example of the operator new last week or the week before. Do you guys recall? Just because we use new doesn't mean we got to call the constructor, right? We can allocate the memory for a memory pool, and as your game advances, you are managing the memory and making sure that the appropriate constructors are going to be called using that specific memory. So we don't really need to initialize. The more important thing is what happens when the function terminates, what happens when the exception is thrown. How does this guy die? Right, so less to do with initialization and more to do with the the death part, right? And so, but I have my mental way of thinking about this is actually quite simple, and I'll help you I'll share that thought with you guys in a moment. But the basic thing is that it helps avoid resource leaks, and it makes your code be exception safe. This is quite important, guys, because with games that are running on your computers, it's okay. You don't need to worry about exceptions. If the game crashes, it crashes. But banking software, anything complicated, right? The system needs to be on 24/7, and it needs to kind of log errors and maybe degrade and come back up. So error handling becomes critical, and you cannot do that in C++ without doing this, right? Without using this particular idea. So the way I think about it, okay? So let me explain what that means. Why I still don't quite understand why it's called resource allocation as initialization, but I have my way of thinking about this. So think about this. You have a really big program. I threw some numbers, right? You're making allocations of 45,678. Notice the nice 4, 5, 6, 7, 8, right? Memory blocks. What's a memory block? It could be 1 megabyte, 1 kilobyte. It doesn't really matter. But you're making a lot of calls, right? And you're doing this in these many program locations. So we are really looking at a non-trivial program, maybe written by hundreds of people. So how are you going to be able to confirm that all memory blocks are free? And remember, in these sorts of non-trivial programs, there are a lot of other resources, right? Files, network sockets, so on and so forth. So how can we confirm? Well, Valgrind can try, but we cannot rely on Valgrind, right? Because it can only find certain things. It cannot find certain insidious errors. So in my opinion, right, what is beautiful about the paradigm that is called RAII is that with this particular system, right, if you are making 987 in 987 places calls to new, let's say, array, there are 987 other places that need to catch our call delete, our delete array. Am I making sense? And trying to keep that correspondence without making these double deletions, premature deletions, is the critical problem, because we make calls to new in one portion of your program, and the deletes can happen in a completely different program. And these different regions of your program could be authored by different people. But if we think about RAII, well, there's only one object, right? The single local object that is given birth when your function is called, right? This object gets to claim some resource via its constructor. And when the function terminates, this particular object's destructor is automatically called. So the same guy that does the new is also doing the delete, right? So they're completely perfectly paired. We don't need to go hunt. Hey, where did we do the new? Is there a corresponding delete? Because that is the sort of problem, that happens in much of commercial, in the real world software development, life cycle. But here, when we come in here, all we need to do is organize our file pointers and instantiate objects that come alive within the scope of that particular function, and they're automatically going to die. No need for pointers, right? Absolutely no reason to have any sort of pointers unless those pointers are wrapped in low level classes, such as a string class or a vector class, or a thread class, a mutex class, and so on and so forth. And in my mind, the way I'm thinking about it is that RAII, I think, is an application of what is called the single responsibility principle. We'll look at it in the second half of the semester. It's a software design principle which says if you're going to build a class, design the class to do just one thing. Just one thing well, right? If you have one single class dealing with 10 different things, they have a name for such kind of classes. They're called God classes. And with God classes, you end up with the same problems that we spoke of earlier. When you close your file handle, well, you also need to worry about all of the other resources, because otherwise you're going to have a leak. On the other hand, in our file pointer scenario, this guy takes care of nothing except file handle, and only one file handle. And so it can author its constructor and destructor, in a very simple fashion. And it doesn't need to deal with all of the other resources that might exist in your system. So this is my understanding of what RAII means, right? And this is an important thing. We don't need disparate parts of your program to be connected. Instead, we have one single object that takes care of both the new and the delete, and it's in one function, right? And the behavior of that function can be easily analyzed by looking at its constructor and destructor. And if we implement those correctly, then chances of getting a leak are minimal, right? It doesn't matter how complex your system is, because the C++ runtime mechanism takes care of calling your destructors, excuse me. So there's never any chance of a leak. And that also leads to the idea of how can I write code where I don't use any pointers, right? And that is again connected to the idea of smart pointers. Okay, so I thought I'll illustrate what I mean in terms of a picture. In this particular function f, The new and the delete are sort of close by, but generally it may not work like that. You may return W, right? Or F might return W to somebody, and that somebody may pass it to somebody else. And it continues that way, and the distance between the new and the delete, if the delete ever happens, can be humongous and hard to decipher. So this is the situation. Well, V came alive via its constructor. It got its uh, data members properly initialized, and they in turn acquire some resources. The same thing happens for W, but W is indirectly pointing to a object of type X, which in turn acquired some of its resources. So W is the problem now, not F, right? And if we don't have the delete, then essentially you end up with this scenario, but this guy automatically vanishes completely, right? And that is the beauty of it. So maybe if I couldn't explain it well, hopefully this picture captured the essence of it, right? The data that is pointed to, or the resource that is pointed to by W, is lost forever. So if you're working on a huge environment that serves as the backend of a banking system or any such system, at a certain point, it's going to crash. Now, there are some guidelines, right? And I'm going to kind of explain. I've already talked to you about this. The resource handling class should not manage more than one resource. One example is a file pointer, right? And in my mind, the motivation is that, hey, if there is an exception, then the constructor doesn't need to worry about any other resource. And I have actually some code where I can show you how this works. Suppose I have a class where we have two resource handling class members. One could be a file pointer that we wrote, and then the other is the string class, maybe that we wrote in HLP2. So each one deals with two different kinds of resources. So it's okay to create a new class, to define a new class where each one of these serves as a data member. And so the motivation is that if the file pointers constructor throws an exception, well, it itself, the file pointer, doesn't care about the string. The string likewise doesn't care about the file pointer. And the C++ mechanism will take care of the containing object being properly destroyed. And I'll show you what I mean by that, because that could be a little bit hard to understand. But let's try. If the first member is constructed, okay? So I have a class that contains. So we are talking about has a relationship. This particular containing class has a file pointer member. It has a string member. Now let's suppose the first member was constructed and the second member throws an exception. The string class threw an exception because there wasn't enough memory. The C++ exception mechanism will make sure that the destructor for the first member is invoked, but not for the second member. In other words, it's doing some magic in the background. And what they promise is that this magic is not going to be expensive, right? So somebody is keeping track of which destructor got completed and which destructor hasn't been completed. And it will make sure which constructor I should say. So it will make sure that it'll remember that the first member's constructor was completed, but the second member's constructor threw an exception. So it will go in and call the destructor for the first member and obviously not call the destructor for the second member, because that is going to lead to calamity, right? Because you have an object that isn't properly constructed and you're calling its destructor. Now, let's suppose in the containing class, both members are constructed and the constructor of the containing class is still doing some work and it throws an exception. There will be no leak since both members, since they are fully constructed, will have the destructors be called. And we can actually write some code to kind of understand these things. If you build it like this, then chances of people complaining about garbage collection and all that other stuff, right, will go away because we're taking advantage of C++'s mechanism. And I'll also show you an interesting thing. So let me go to the code. I've already written it. I'll throw it online after the class is over. I think it is here. All right, so this is the file pointer header that I showed you guys. Nothing much has changed. It is exactly what I showed you. The only thing I did was, as you indicated, I deleted any copies because that is bad. And I just put the debug statements to print. All right, so I'm encapsulating a C-style handle. What are the other things we have there? Let me show you the string class that we are familiar with that I kind of use extensively in HLP2. Right, this source code is anyways available, but I'll also put it online. So all of you should remember this because this is kind of how I teach HLP2, because this guy contains everything we need to know in terms of class design, right? So it's got nothing much going on. Default constructor, just a conversion constructor. I'm just throwing these names out so that everybody's clear. This is just a regular constructor, a destructor, and to keep track of how many there are, sometimes for debugging, when we are learning new things, I find it useful to have a counter of how many objects have been created, right? So I can keep track of constructors and destructors. So this is the implementation, pretty trivial. And so nothing much going on. All of you have seen this before. So now let me show you the new class that we are going to design. So I call it, I'm not sure what I call it, X. Okay. So this particular class is being built. It contains, it has a file pointer and a string class. This guy deals with file handles. So this guy, the string class, I just call it mstring. I'm not sure why, but to differentiate it from the regular string. And I call it, so we have two guys, one deals with file handles, the other one deals with another resource, which is memory. Okay, so I came up with some very, silly constructors, but here we go. So this is a constructor. And notice this constructor is simply taking the name of a file and whether you want to open the file for read, write, or append mode. And this is the C style string that this guy must encapsulate. So it's easy enough to write the constructor using a member initialization list. Okay. Then I decided I am going to have the ability to create a string with these many characters, each character having this value. Okay, so again, not a complicated function. And so this is constructor 1, constructor 2. Now I have a third constructor. Okay. throwing. Okay. So there's the third constructor. And it basically, is just an overload, right? It takes the name of a file, the mode in which you want to open the file, and it takes a C style string and some size parameter. Why? Because I want to inject some exceptions, okay? So this guy basically uses it's a delegating constructor, right? The one we just saw earlier. And it is using this guy to, do the work of construction. Now this is my way of making sure that after the object, my two data members are completely constructed, it's my way of injecting an exception. This one is going to create an exception if I call this n with a really big number, right? And we'll do that. And so during the execution of this particular constructor, after both data members are completely constructed, we are injecting an artificial exception, okay? Now, I want to show you one thing. This one is a new constructor. What it basically does, it says, give me a string that contains these many elements, each element initialized to this, okay? Now, when you write these kinds of classes, unlike in HLP2, anytime you call, the new operator, you have to worry about the new operator throwing an exception, right? And you can't just assume that there's going to be enough memory, because then your class, if it's going to be used by somebody like X, is not going to work out because X assumes that you guys know how to deal with exceptions, right? And it assumes that you are RAII classes. Okay, so here's something interesting for you guys. How do I write the constructor for this using a member initialization list, but still catch exceptions that are thrown? So this is something interesting that you haven't seen, and I'll show you this particular feature. So this is the function, and you have this weird try. That's fine. This is the member initialization list. All of you know what that is. And what I'm doing is, just like I did in HLP2, I'm initializing the length data member with the value associated with this parameter. And then I'm allocating certain amount of memory equivalent to whatever this length member contains or specifies. And that particular return value to the first byte of the allocated block is going to be used to initialize pointer. But what if in this member initialization list, this guy throws an exception? How are we going to catch it? We know how to catch it in some of the examples you saw, right? We know how to catch it in the body of a function. We know how to catch it in the body of this constructor, but how do we catch it in this particular member initialization list? Because if an exception is thrown here, you cannot catch it in the body of the constructor because the execution will not get to that point. Stack unwinding will take place with whoever invoked this constructor being where we begin the unwinding of the stack. So C++ gives this really weird syntax. that allows you to catch an exception with our enclose an exception in a try block like this, right? So the member initialization list begins with the colon. So before that, throw the keyword try. Then write your member initialization list. And then write the body of your, all the way here, write the body of your constructor here. And the catch clause associated with the try for the member initialization list comes here. It's kind of a wacky way to do it, and it's not very well known, but if you are interested in building an RAII class, anytime you're grabbing resources from the system, you cannot wait to get into the body of the constructor to see if an exception was thrown, because you're never going to get there. So the only way available is to enclose the member initialization list in a try block. Okay. So that is what it looks like. And if the memory cannot be allocated, then this guy will catch the bad alloc that is thrown, and then we'll end up printing this and throwing that error back, because we want the stack to unwind, right? We don't want, the system to assume that the constructor was properly constructed, because it wasn't. So we need to make sure that we throw again, and somebody takes care of the bad alloc. Okay, so there is a way now for us to create all these different exceptions and test the behavior of our RAII class. Okay, each one of these is an RAII class, because this class X has as its members RAII classes. It doesn't need to do any work to take care of RAII, because it has delegated that work to its data members. And that is the beauty of it, right? So you never ever have to create objects of type pointer to X in your code, right? If you are using pointers, instead you create objects of type X and make sure that these objects are local objects, and RAII behavior kicks in. All right, so here, obviously you'll have to spend a little bit of time when you get home to kind of look at it, but this is main. So I'm creating X1. This one doesn't throw any exceptions. Instead, it's going to create this particular file for write, excuse me. And it's going to create initialize the data member S of X1 to encapsulate this string. So nothing bad is going on, right? And you can actually compile and see what's going on right here. Yeah, let's kind of, there's some debug messages in case we are interested. Then what is the name of this file? RAII. So basically this is saying the file pointer constructor went through, so the object got constructed, data member F. This basically says data member S got properly created, and the entire constructor associated with the containing object X has successfully completed. And without us doing any work, all of the resources are going to be returned back, right? So that is classic RAII behavior. Okay. So now we want to inject some bad stuff. This is a hack that allows me to do that. String class, okay, has a function called max underscore size. I believe it returns the largest value that can be represented in an unsigned log, which is a big number. And my computer doesn't have the memory, right, to store that many characters. So the maximum size is something that is not possible on my computer. So I'm passing that number to construct this guy. Okay, and that constructor is going to be no, I should be looking here, isn't it? So the constructor 1, 2, 3, 4 parameters. So it's going to be this guy. No, it's this guy that is going to be called. So this is setting up the file pointer, no problems. And this is calling the string constructor to initialize S. And that particular constructor takes this really large number and the character that needs to be replicated across every single element. And obviously there's not enough memory. So when we come in here, it is going to throw an exception. So I need to go to the try, yeah, this one here. So this guy is going to throw an exception, and the exception is going to get caught by the catch clause associated with the member initialization list. And the throw is going to be propagated back up, right? So with the stack getting unwound. And so when I get into RAII, this is not constructed completely. Everybody, no, not this guy. Yeah, hang on. Yeah, this guy is not constructed completely, right? The F data member of X2 got constructed, but not S. So what we want to see is the runtime environment calling the destructor for the F data member, but not for the S data member, because the S data member never got constructed. And we also want to see the destructor for X2 not being called, because obviously we didn't completely create the object. The construction of the second data member or the initialization of the second data member through an exception. So that is what we would like to see, right? And so let's go see what's going on. So I'll put a return here just so that we demarcate what's going on. Maybe I'll put the return after this as a marker. Okay. All right, this one is the good guy. As you can see, both the F and the S data members, and obviously the entire constructor, everybody got successfully created. Now, with the second one that is enclosed in the try block, the F data member got initialized. The S data member did not. Instead, it threw an exception that was caught by the catch clause associated with the member initialization list. And notice that the destructor associated with the F data member is called, but the destructor or even the constructor, none of the stuff related to X is being printed. So X wasn't constructed. And still, we didn't have to deal with it, right? The runtime mechanism used our well-designed RAII classes to get all the work done in terms of cleaning up. So you can see here that the earliest object that got constructed, it is finally getting destructed. This guy, well, there's no memory that has our resource that is left lying around because we threw an exception during the construction of that particular object. Am I making sense, guys? It's a pretty cool thing. You know, if you're not sort of getting the sense, and it is kind of something that could be obviously pretty useful in an interview, especially because most companies, they do sort of more how should I put it, non-trivial code, maybe a couple of factors above your games, and some of that code has been around for years. So it's production code. It is actually code that makes people money. And so they are very interested in obviously these sorts of things, right? So are there any questions that I can answer? Am I making sense to anybody at all? Because happily I forgot that I was talking to anybody and I just talked, but don't want to talk into a vacuum. Am I making sense, folks?
Yeah.
All right. At least to one person, okay, which isn't
two.
Sorry?
No, I said yeah, so
So 2, okay, all right. And I'm sure we have a silent majority. Okay, so then this is the last example that you can try when you're home. And what I do here is that the construction of both the data members of X2 are complete, but we are injecting a sort of artificial exception in the constructor associated with X2, right? Just let's just look at it because all these are quite interesting things. I need to go up here. Sorry. It is this guy. All right. What I'm doing here is obviously both the data members are properly constructed, but I come in here and I say, hey, give me a string. And this string is going to be this humongous number that cannot, memory for which cannot be allocated on my machine. So we end up with what is called a length error, right? It's actually thrown by one of the constructors associated with the string class. When you specify a value that is too big, right? Not enough memory exists. And or maybe a number that is larger than the max size, right? So we get a length error. And so we need to pay attention to what's going on here. Both the data members got constructed, but we couldn't complete successfully the construction of X2 itself. So let's try it out. Oh. All right, so this one is the first one that is good. This one is the bad one. Now notice with this one where I'm injecting in the constructor for X. So this guy constructed the data member F successfully. This one constructed the string data member successfully. This one, so notice I'm delegating the job, right? To some other constructor. So the printout that we see, excuse me, the printout that we see is for the delegated constructor. And notice that the destructor associated with X, the object that we wish to create, is being invoked. Okay, let's take a moment to look at that because that's interesting. So we delegated the work of constructing the data members of X to this guy. This guy came and then, we did some work here and this threw an exception. So who's catching the exception? So we come down into main and we see that the exception is being caught by the try block. So the catch block is going to come in, right? And the runtime environment, notice the beauty of the entire system is that we come in here and the runtime environment says X2 did not completely complete its construction, but its data members were properly constructed, right? So magically it knows that both data members were properly constructed. And in this particular line that you see here, the output, it is actually calling the destructor, because that is the destructor's job, to call the destructors for the two data members, right? Which it does. And you can see that the two data members destructors are called. And this shows you that even if the objects constructor didn't get fully executed, the system is able to keep track of which objects were constructed and which were not. And this probably also ties into something that I tried to kind of spend a bit of time talking to you guys about. I'm not sure if you recall, but let me pick a simple constructor, right? Do you guys recall that when I spoke to you guys about construction, I said, when you get to the opening brace of the constructor's body, construction is done. Do you guys recall that? And I also said that is the reason why we need a member initialization list, because the actual initialization of the data members takes place before you get into the body of the function. The body of the function is saying what needs to happen after the data members are initialized. And that is also proven right in the output that we see, right? So another little nugget of fact or information. Try not to write any constructor without using the member initialization list. And there's no excuse now, because you can actually catch exceptions even in the member initialization list. And remember, all initialization has been completed when you get into the body of the function. So these are, this is the particular thing that I wanted to talk to you about, the guideline, right? So make sure you kind of pay attention to this if you're interested in writing sort of classes that are RAII. Okay, the next thing you want to do, and this is also important, is don't throw any exceptions from destructors. I mean, think about it, right? So this is an example, but we can come up with any number of examples. So my widget contains all kinds of constructors, but it has a destructor. And look at the comment there. It says this guy might throw an exception. Okay, the standard itself doesn't say, you know, you can throw an exception. So this is a guideline, and actually a pretty strong guideline. It says do not throw an exception. Right now, you might ask, why doesn't the standard, you know, prevent us from doing that? I have to kind of do more research to find out why. But the important thing is, we have this function foo that gets called in this try block, and this function foo creates a vector of 10 widgets. Okay, and then we are using these widgets. Obviously, when we reach the conclusion of function foo, the vector class is going to say, I'm going to go through each one of the 10 elements in my dynamically allocated memory, with each element containing a widget, right? I'm going to go ahead and destroy each one of these widgets using the destructors. So it does that for the very first object, calls the destructor. But that destructor throws an exception. Now we have a real conundrum. When you throw an exception, stack unwinding takes place. So the compiler is looking for who can catch this exception. Obviously, it finds an it finds an exception here. It finds one here. So it's going to have to unwind the stack, everything associated with foo, and then do nothing after this line and essentially end up in the catch clause. The problem is it is in the process of deleting 10 widgets. It only deleted the first one. And there is a real conundrum. Should I go chase the corresponding catch, or should I get the stack unwinding, or excuse me, the other 9 widgets to be deleted? And obviously that's between a rock and a hard place, and your compiler is simply going to crash and burn, right? Not literally, but it's going to go ahead and call the terminate function, which means you're not performing a graceful degradation. Instead, you're abruptly terminating, which means there has been no time to flush all of the caches from memory into hard drives and so on and so forth. And so quite a bunch of information is lost, and your system is now in a completely inconsistent state. Am I making sense here, guys? So do not write anything. Do not write any code that might potentially call a throw an exception. What could throw an exception? Well, calling one of our mstring, right? Instantiating an object of type mstring. That guy allocates memory. If there is not enough memory, then it throws an error. Sometimes it throws a length error. So we don't want to do that. In fact, by default, all destructors are called no except. This is an important concept. You don't have to add this. Looking at the standard, my understanding is that all destructors are implicitly labeled as no except. Okay, what is this? It's a keyword. What does this qualifier mean? Basically, as I just explained, there are many things that go on in the runtime exception mechanism, right? They claim that it doesn't cost you much, but I'm pretty sure it does, right? But nothing is free. C allows you to do this using what are called error numbers, right? And generally speaking, I would say around 60% of any product that you're going to work on in the real world, okay, is going to deal with this sort of, boring stuff. How do I recover from errors, right? And a huge amount of money and time is spent on that. Now, all of that takes time. So when you add this particular qualifier after a function, what are the functions that you might add this to? Well, in the string class, maybe you have a member function called size. Size, as you're aware, simply queries the length data member and says, these are the number of elements that I'm encapsulating in the C style string. That is not going to throw an exception. And if you qualify your size member function with this qualifier, the compiler knows that this particular size member function will never ever throw an exception, and therefore it can perform some optimizations. So one of these days, what we should do is we should write code that measures some useful functions that are frequently called, that are labeled with the qualifier no except versus the same functions without that particular qualifier. Qualifier. Okay, I said that right. Qualifier. I don't know. My thoughts are going to broccoli and cauliflower now. What was I saying? Yeah, we need to run some profile tests to kind of see how much you gain. So when you are writing code in your classes for all your games and whatever software, make sure that if there are functions that will never ever throw an exception, okay? You should know which functions throw an exception. The ones that deal with resources, right? For example, a call to new, a call to build a string using a certain number of characters, that might throw an exception. So therefore, if you're calling that sort of a function, then your function cannot be labeled no except. But a function such as size, length can be labeled no except, and you will gain substantial benefits, right? I'm quite sure of that. I did some profiling and I'm going to dig that stuff up somewhere on my hard drive and we can look at that. So this is a keyword that is related to exceptions, and please use that as liberally as possible to make sure that the compiler will know which functions are going to throw an exception and which ones don't, and it can therefore optimize the runtime behavior of the ones that don't throw, that is. Okay, so if you follow these two guidelines, guys, I mean, in addition to all the things about class design, I think you should be in good shape in terms of implementing a RAII class. Now we have around, when does this class end, guys? Because for some reason I have to see, but how come you guys forced my computer graphics class to end much earlier? That is the conundrum. That is the $1 million question. Can somebody answer that? All right. I've investigated, and apparently the class should end between 40 and 50. And the remaining 10 minutes are for you to move from one class to the other class, which sitting at home basically means grabbing a coffee, a drink, whatever, and coming back and starting up on the next lecture. Okay, so we are not going to go until 11 because some teachers are getting very annoyed with me. All right, guys, I thought I'll kind of go through a simple vector class rather than a string class, right? And what I want to do is kind of slowly move into Mu semantics. But before we jump into Mu semantics obviously give you some optimizations that are implemented by the compiler. My what I want to give you sort of some focus on is what other optimizations are provided by the compiler. So there is a particular class of optimizations called copy elision, right? ELISION. It comes from the English term elide, ELIDE. Elide means shift, right? So copy shift, which basically means we are not performing certain or making calls to the copy constructor in certain scenarios. If you understand that, I think your code can be written in a much more optimal way, right? And I'll give you a couple of pointers in relation to something that might work for your games, because Windows does things a little bit differently than GNU. All right, so this is a class. Okay, and the reason I've drawn this class is sort of like a short overview of class design and also the behavior of the of the resource manager, because that's what this guy is. Vec is somebody who manages who manages memory that got allocated at runtime. Okay, here we go. So first of all, you'll see that compared to HLP2, we have a nicer way of designing and implementing classes. As I explained in the previous lecture on uniform initialization, we also have what are called default member initializers. So what that means is that if you make your constructors be default, then your data members will always be initialized to these values that you specify, right? So for that reason, the convenient thing is that I don't have to kind of, implement my boilerplate default constructor. Instead, I simply say default. And what happens is that length and pointer are initialized to this. What happens if you have some other constructor? Well, if you have some other constructor and you do something in the member initialization list with these guys, then whatever you do in the member initialization list has precedence over these initializers. Okay, so that makes it easy. It means if you do something in your constructor's member initialization list, then that is what is going to happen rather than the default. So the other thing is that convenience. Notice we don't have to provide any of that stuff related to the default constructor, and it makes your code be simpler and therefore have less bugs. So I implemented a pushback function. All vectors, obviously, you can insert additional values, and in this case, it's a integer value by using some boilerplate stuff. So you can clearly see what's going on. And if you can't, I have some pictures that illustrate what's going on. So this highlighted piece of code is initializing a stack-based local object, right? Clearly, you can see the opening and the curly braces. So this is happening within the scope of some function. And then default initializers are initializing the two data members like this. It's clear to see. Now the pushback function clearly is saying, okay, we already have some memory allocated. I'm going to allocate one extra element than what I have. I'm going to copy from the old location to the new location, get rid of the old location, and make the new location be the new resource. All right, and at the end, I conclude by making sure that my length data member is appropriately incremented to account for one new value pushback. Okay, any questions? So the picture looks like this, and then it looks like this, and this is the memory that got released. All right. Now what happens? Clearly, the compiler is going to synthesize a destructor. That destructor doesn't really do anything. And obviously, the object is gone. And the pointer that was pointing to this resource no longer exists. So we have a memory leak. And clearly, we can fix that memory leak by making sure that the RAII vector class, that's what I want my vector class to be, an RAII class, so that it can be then placed into as a member of other classes. Although I must admit,
Actually, I'm a bit confused now. If the destructor calls, if the vector calls destructor in that scope and the
destructor is it's a synthesized destructor. The compiler will create one.
but
Because
the elements are objects and not pointers.
yeah, so we are here, and as soon as we get there, the destructor has cleaned up the data members, and the reason why you see my object disappear is because it is going out of scope. That is how the function semantics work, right?
So would there be a memory leak or not?
This is a memory leak. Memory leak because there is no destructor that is reclaiming the memory that was allocated in the construction.
But you push back integer values of 1 and 2. Wouldn't that one also cause destructor? I thought it's only pointers.
No. These, this is a, let me clean this up. This is a simple function that encapsulates a dynamic
okay,
array of
it's not the
pointers.
std vector. It's like our own custom vector. I got it.
Yeah. I mean, we want to know how to build an RAII class, right? And I want to use this when we talk about Mu semantics and so on. So, any questions?
No, I understand now because it's a different vector class.
Yeah. So the end of the scope has arrived. So it means that V is going to disappear, but before it disappears, its destructor must be called. But there's no destructor, as you saw in my previous slide. So the compiler will synthesize 1. And what does that synthesized version do? Nothing. In fact, if you have an empty class, okay, I might have said this in HLP2. Nothing, no data members, whatever, the compiler will synthesize. All right, a destructor for you. And what does the destructor do? Nothing. And that is the reason why we end up with the memory leak. The memory that got allocated by the 2 pushbacks has not been reclaimed. Each pushback function, okay, it's quite important for everybody to understand each pushback function is correct. It does the proper thing. It allocates appropriate number of elements, 1 plus the previous size. It copies all of the data from the old into the new. It makes sure to return, deallocate, or delete the memory that the memory from that contain the old data. And then this one is making sure that the pointer is now pointing to the new block of memory. And this got allocated. So none of the problems here are related to the default construction, nor are they related to the implementation of the pushback. The simple fact of the matter is if you want an RAII class, as we just kind of looked at all day today, you need to have a class that contains a constructor and a corresponding destructor. So we didn't write one and we ended up with a memory leak. So let's go write one. And it's pretty simple and straightforward.
Is this considered application of rule of 3?
Of what?
Is this like application of the rule of 3?
Yeah. So rule of 3, yes. So we have the vector class now containing a destructor. So beautiful slides. I'm really proud of my work. So I'm going to continue and you can see we have a problem. What is the problem? Well, it wasn't with vector V. It got constructed properly. Right? Not the pushback, which is implemented correctly, but it went into a new scope that contained the definition or the initialization of a new object called W. How does this initialization take place? Do not be fooled by the presence of the symbol, the equal to symbol. Basically, it is not the assignment operator nor the equal to, it is simply a separator that says, I would like to be copy constructed, right? So the compiler will say, OK, let me go ahead and synthesize a copy constructor. And since you didn't define one, I'll synthesize one. And what does the default copy constructor do? The synthesized version, it takes a bitmap of the right-hand side and copies it over to the left-hand side. I'm sure all of you are pretty well aware of this, right? So we have a problem here because we in fact have both V and W pointing to the same resource. And remember the double deletion problem that we spoke of, our premature deletion. So now when we reach that particular location in your code, V is going out of scope. That means that the destructor associated with W is going to be caught. Right? W is the one going out of scope, and that's why I painted it red to indicate danger. Why? Because W is going away, but its destructor is going to claim this memory and return it back to the free store. So think of it as a premature deletion and W is gone. So now V has no idea about any of this stuff. So V merely goes along and tries to access the memory that it allocated, and obviously who knows what might happen. Undefined behavior, right? Anything's possible. So that is where we are. And then notice another bug. We already deleted the memory and V is going to go out of scope now, and its constructor is going to come in and call the delete array. And so you end up not only with all of the previous problems, but a new problem. So you can imagine the state of your system is in terrible shape after all of this. So there you go. So what we need to do is we need to build what is called a copy constructor, all right? And this particular copy constructor doesn't do anything. It just simply allocates the appropriate memory. And remember, guys, if you want to build real RAI classes, I've shown this in my other code, you need to throw if there is an exception raised by operator new. OK, you got to. This one, no. This one, no. But this one, you got to catch. Right? OK, so you allocate the memory and then you use the standard algorithm to copy all of the contents from the previous to the current. OK, from the right hand side to the left hand side. So now we have sort of like a class that is getting closer and closer to the ideal class. Now I have, one more problem that arises. Notice that we have V well defined. We enter a new scope. We have an object W that is default constructed, as you can see in my picture. And then we have the assignment of V to W. And this is done through what is called a copy assignment operator. And the compiler doesn't see one in the class declaration the definition of the class associated with of the class called vector. And the compiler will therefore synthesize a copy assignment operator. And what does it do? Again, it takes a bit copy associated with this and essentially copies it over. So this is going to be 1, and this guy is going to contain the same address as this guy, and that is what these arrows are showing. They're pointing to the same location, and obviously, no surprises, it's going to cause a whole lot of problems. So we have what is called a shallow copy. What we should have done is a deep copy, which entails allocating all of the memory associated with this particular handle or resource and making this guy point there. Right? We didn't do that. So we instead, rather than performing a deep copy, we performed a shallow copy. So W goes out of scope, and the resultant premature deletion is going to play havoc with V, because V is accessing memory that no longer is private to it. All right, so premature deletion and undefined behavior. All right, so we go and build a copy assignment operator. OK, and this is essentially called the rule of 3, because if you are defining any one of these three functions that you see here, the destructor, the copy constructor, the copy assignment, you have to build the other two, right? This is called the rule of three. And the only thing I'm going to say is that I'm using a slightly different way of implementing the copy assignment operator. In HLP2, I did all the boilerplate stuff that mimics this, but there is a simple idiom that is common among C++ programmers that says copy swap idiom. Right? So what are we doing? Well, basically, I'm making a temporary copy of the right-hand side. This is done by calling this constructor. So copy contains a complete clone of the right-hand side. Now, the clone copy is calling a swap function, a member function that is not shown here, but that must be implemented, that swaps the copy's two data members with the object pointed to by this pointer. So copy contains what this object wants, so that this object says, okay, give me your stuff and you take my old stuff, which anyways needs to be destructed, right? And when you return, that is what's going to happen, because this is now almost an RAII class. So whatever resources that it is claiming or has claimed simply through the swap will now be destroyed using the vec class's destructor. Okay, so if in the midterm I said do not use the copy swap idiom, it basically means don't write these three lines. Okay, and don't, right? Because I want to make sure everybody knows what that means, the copy swap idiom. So this is the rule of three, and then we'll take it up from there in the next class. How's that? Any questions, guys?
Yeah, that sounds good.
Any questions?
If we don't use a copy swap idiom, we'll do a different way to
Well,
do a deep
obviously, HLP2, what we did was we said, okay, create a temporary.
Yeah, we create temp and then we assign temp.
Yeah, we do all the boilerplate stuff, which is all of this stuff, right? Which is got to be moved down here. That's all. This is simply an idiom that makes it easy. And also, if this guy is an RAII class, it will take care of any exceptions that are thrown. You don't have to do that inside the body of this assignment operator. Remember, we are doing all of this because we care about exception safety. Am I making sense? And the second reason is it also takes care of self-assignment. So these are my two favorite reasons for the copy swap idiom. Okay. Alrighty, guys. Have a good day.
Instead of the midterm, we might not have to use it, so we have to use the HLP2 deep copy method.
Yep. If you use the copy swap, then first of all, you're assuming that the swap function exists. Maybe I'm not going to author that. So then you don't have an opportunity to access the class definition, so you can't author a swap. All right, so next class, I'll talk to you guys about copy elision, which is a type of compiler optimization, and move semantics, which is a second type of compiler optimization. And if you have time, I guess we'll get going with smart pointers. Not just how to use them from the library, but also how to build our own if you're working in an environment such as an embedded system where the library is a bit too expensive. All right, guys, thank you very much. I'll see you guys
Professor, is there consultation later?
today. When is it? At 7, right?
Yep. Okay.
Hang on. Actually, there's no more going to school because my class from 3:30 to 5:30 is online. So I'm going to move the online sessions to 6 to 7, okay?
Okay. Sure.
All right. I'll send a note.
Okay. Thank you.
Very welcome. See you guys. Thank you very
Thank
much.
you.